kids, look what I found in my attic, right? I had to take a picture of it. I was looking up in my old boxes and records. Do you even know what a record is? And look what I found. This old record I had, and it says it's Unit 7 of combinatorics and probability. Oh my gosh. Who would have thought? Kind of crazy, right? All right. So this unit, first unit of your second semester, really, right? Since we've finished with the cumulative, good job, by the way. So Unit 7 takes a little break from continuous math. Continuous math is basically your entire, right, middle school to high school mathematics. It is algebra to calculus based. Discrete math is a whole separate branch of mathematics. I took an entire college course called discrete mathematics. Some colleges call it different things. If you definitely will have to do discrete mathematics if you're in computer science. You will do a unit in this in HL math, and it will be it is on both the SL and HL math exam. And the HL just goes a little further. So discrete math, how it differs from continuous is that if I give you an interval in continuous math, 0 to 1, in between here, there are an infinite number of values, right? Right? We have a half, we have a third, a fourth, a fifth, a sixth, a seventh, a eighth, a ninth, a 10th, 11th, 1/12th, right? Forever and ever and ever and ever and ever. An infinite number of values between 0 and 1. Discrete mathematics says, I've got 0, I've got 1, and that's it, right? There is nothing between 0 and 1. It jumps from 0 to 1. Get it? Binary, true, false. 0, 1. Discrete mathematics. So there's a whole different, as I said, branch of mathematics, different theorems, different, that apply when you have discrete values as opposed to continuous values. So 99% of this unit is going to all be on discrete math, and it talks combinatorics, counting, probability, and at the very end of this unit, we'll do one thing that kind of ties together discrete and continuous math, right? And kind of takes you back. How do I take discrete and still do some algebraic manipulations with it? But first, we're going to start very basic. Counting and permutations is part of, even though this is our Unit 7, this is Chapter 9 in your book. So the first section, we're going to talk about counting and permutations. So discrete mathematics, I have a discrete task, and I can perform that task in so many steps. Those are discrete things, discrete situations. So I can make this sound so funny, fancy. Assume a task can be broken up into S sub n consecutive steps. If S sub 1 can be formed in N sub 1 ways, blah, 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 blah. Here's what I mean by this. Here, Victoria has bought 3 new shirts, 4 pants, 2 socks. How many new outfits does she have? Right? There are 3 discrete shirts. 1 shirt, 2 shirt, 3 shirts. When she makes a new outfit, she will choose one of those 3. When she chooses a new outfit, she will choose one of the 4 new pants. And when she chooses the pair of socks, she will choose one of 2 new socks for a total of 24 possible new outfits. Right? Notice what's in between here is multiplication. This is the multiplication principle of counting. Sounds so fancy. Look how cool I am, and I'm just counting. Here's another classic example, right? It could be social security number. It could be license number. It could be license plate number. This is a policy number there's policy numbers for, insurance or whatever. A securities company is like a Wall Street thing, bonds, or I don't know, something like that. Doesn't matter. Here is the form of labeling each different one. The first character is a letter. The second character is a non-zero digit, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And the last 7 digits are any numbers, so 10, right? Because in just digits 1 through 9, I'm adding the 0. So each one of these slots is a choice I can make. I'm going to use the multiplication property of counting. So I'm going to multiply in between all of those. How many choices for the first slot? In the first slot, how many different ways can that be achieved to get a letter in there? 26, right? For the second slot, second task, how many different ways can I perform putting a digit from 0 to 9 in here? How about the third through the 7th task? How many different ways can I get a digit not including 0 in here? And the same for here, 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 and here. I could write this as, and I wrote down this somewhere. What did I get? It was like ridiculously large number. Right? Good? Just counting. Now I want you to look at this last part. What if I just wanted to know about, what if I just wanted 9 slots and I wanted to fill them with the digits 1 through 9? How many ways are there to arrange those? Right? So instead of 7, I want a slot for each 9 digits. Each of the 9 digits, I'm sorry. So I could choose 9 in there. And what are you doing in between there? Multiplying. This is a bit tedious. Repeated multiplication of the same number can be written as exponentiation, right? I didn't write down what that was, whatever 9 to the 9th is on my calculator. Well, look at the difference in this question. How many ways are there to arrange those 9 digits, right? 1 through 9. How many ways are there to arrange without repeating? Without repeating. So I still have 9 digits. I still have 9 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm still going to multiply. So I'm still using the multiplication principle of counting. But how many ways can I perform the first one? Right? In here, I can put 0, I can put 1, 2, 3, 4, 5, 6, 7, 8, or 9. But if I'm not allowed to repeat, how many choices do I have now? And then now. So still the counting principle, but the multiplication principle of counting, but we have a different name for this because I need to make sure I remember without repeating. Without repeating. Permutation of n things is the word for counting without repeating. There are n exclamation points permutations. A synonym for permutation is arrangement for n things. So this exclamation point has a name in math. It's called an exclamation point in English, but in math, it's called a factorial. My daughter used to call, when she first learned about this, she called it a yell point, which I think is pretty good. Much better than exclamation point. Call it a yell point, right? So I'm not saying there are n permutations. I'm saying there are n permutations. If you had your earbuds in, that must have kind of hurt. Right? I am serious. No repeating. So this expression, how many ways are there to arrange without repeating? 9 times 8. Now remember, if I just had 9 times, I could write that shorthand notation as 9 to the 9th. I can write this as 9 factorial or 9, right? 9 factorial by definition is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what it means. So what if I wanted to count the number of arrangements? And arrangements is a synonym for permutations, which is counting without repetition. Count the number of arrangements in the word lucky. Well, I have 1, 2, 3, 4, 5 slots for 5 numbers, or letters, I'm sorry. 5 letters, 5 slots. I am going to use the multiplication principle of counting, but in the first slot, I can choose 5 letters, but whatever letter I choose here, I can't choose it again. But of course, I don't have to write it that way. I can just write 5 factorial, which is 120. Now, this wasn't hard to figure out without a calculator, right? 20, 5 times 4 is 20. 3 times 2 is 5. 20 times 5, 120, right? Or 5 times 2 is 10. 10 times 12 is 120, right? You can do that a lot of different ways. But when you get, it doesn't take long before figuring out a factorial or expanding a factorial without a calculator is annoying. So if you have your graphing calculator and you find your math button, which is kind of on the left there below your alpha button, hit math, arrow over 3 times to PRB, which stands for probability. And then choice 4 is your factorial. So on your home screen, if you type 5 and then you do math, arrow, 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 perb 4, enter, you'll see 120. Wait, is this the same question? Count the number of arrangements, and remember, arrangements means permutations, which means no repeating, of the word puppy. Isn't this just 5 factorial? Or 5? No, that's not right. Why is this incorrect? Can you think why? For the word lucky, we were lucky that there was no repeated letters, right? So if I write the word puppy, but I indicate my P's, I have 1, 2, and 3 P's. Whoa, I didn't even finish writing my columns. Look at column 1. Column 1 all looks like puppy. It's all puppy, right? It's just that, but I know that I use the P's in a different order. But if you just are looking at the word without the subscript, you just see puppy. So all 6 of these arrangements look the same. So do I really have 120 arrangements? Do I have more than 120 or do I have less? I have less, right? So what mathematical operation? No, not dividing. Shoot, not subtracting is what I meant to say. Not subtracting. Subtracting certainly makes smaller, but I want to chunk by groups. That is division. Shoot, I gave it away. So this whole column is all my PUPPY column. That's the first column. The second column is all my PUPYP column. How many columns do you think I have? Yeah, 6. Now think about this. How many repeated letters did I have? I see a P 3 times. How many different ways can you arrange P? Permutate 3. Permutate P 3 times. Well, I can put P1 here, or P2, or P3. So this is 3 times 2 times 1, which is 3, which is also 6. That's my 6 groups. So I need to take my 120 arrangements and divide out those columns. So it's 5 factorial divided by 6, Really, it's 5 factorial divided by 3 factorial, which is 5 factorial divided by 6, which is 120 divided by 6, which is 20 distinguishable permutations, right? I can distinguish between PUPPY and PUPYP. I cannot distinguish between all of these because they look the same. Because of the repeated letter, I had one repeated letter, repeated 3 times, 6 different ways that can be organized. So distinguishable permutation has a 2 repeat, right? I already know by permutations, I don't want to repeat arrangements, but this is careful about your repeated letters. So that's what this formula is. Your original 5 factorial, we had 5 letters divided by 3 repeated, right? P was repeated 3 times. Right? So how about bumblebee? What would you do for bumblebee? How many letters are there first? 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. Arrangements is permutations, so no repeats. That means I need factorial. So 9 factorial, but there are some repeated letters, aren't there? The E is repeated 3 times, but what else? The B is repeated 3 times. Nobody else is repeated. So what does that mean? I have to divide off the 6 columns of E's and the 6 column of B's. Oh, my Lanta. Okay, so 9 factorial is much larger than this, but I had to divide off the repetitions for my distinguishable permutations. All right, now look at this problem. Count the number of arrangements of 4-letter words that don't repeat letters. What's different about this? Uh-oh. It just says 4-letter words. In this slot, right, I have 1, 2, 3 slots because I have 4-letter words, but how many choices do I have for each? And it's arrangement, so I can't repeat. So what happens here? I have 26 choices for the first slot. I have 25 choices for the second slot, 24, and then 23. Can I write that as a factorial? I don't think so. Right? Because I can't say 26 factorial, can I? But there is a way I can use factorials to represent this number. And it's going to be convenient to use factorial formulas, I promise. If I want it, because look, before I even answer that, this isn't terrible, right? I could just, especially if I have a calculator, I just do 26 to 20. Okay, fine, equals blah with my calculator. But what if I had 13? Now you've got to type, right? I still have 13 letters, but for each slot, I have starting with 26. So I got to go 26, 25, 24, 23, 22, 22, and factorials don't help me, right? That's kind of annoying. I really kind of wish I had a formula. Here is the permutations, which the arrangements of n things, so think choices, taken r at a time, where I have so many choices to go into these slots. And when when R is less than or equal to the number of choices, there's a formula with factorials that are going to help, so you don't have to just write out, what if it was, my God, what if it was what if I had a million somethings and I wanted 500,000, slots? That's an awful lot of blanks and multiplication. So here's the notation where there is NPR, not the radio station, permutations. This is read n things taken r at a time. And here is the formula. So hopefully this makes sense, right? You have, right? Think about this situation up here. This is not 26 factorial. It's not 26 factorial. Who's missing? 26 factorial would be, what would that be? That would be 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 times 17. Well, isn't that 22 factorial? 26. So my actual answer isn't 26 factorial, but it's 26 factorial divide off the 22 factorial, right? And then you will just have 26 times 25 times 24 times 23, right? If you had 26 factorial over 26 minus how many slots I had, well, that's 26 factorial over 22 factorial, but that's 26 times 25 times 24 times 23 times, oh crap, 22 factorial, 22 divided by 22 factorial, bye-bye, and I'm left with 25, 25, 26, 25, 24, 23, no factorials, OMG, right? That's an awful lot easier, especially when, if it was just 4 letters, who cares? But remember, what if it was 13? What if it was 13? Then I would have 26 letters I wanted to make a permutation of, but I only had 13 slots. So that would be 26 factorial over the 26 minus 13 factorial. And then I just punch that into my calculator, right? 26 math, arrow, 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 perb 4, right? Right? I didn't write this number down. What if n was equal to r? What would that be? What if I had enough slots for enough letters? I really wouldn't need this, but the formula has to, right? Because I would just be doing the counting principle. I would just be doing 26 factorial. So, but my formula has to work. That must equal 26 factorial. How can that equal 26 factorial? There's only one way. What's that way? The denominator has to equal what? 1. Well, what is that denominator? It's 0 factorial, hun. So guess what? 0 factorial is equal to 1, but it's just because we needed it to be. We needed it to be, so it was defined that way. 0 factorial is equal to 1. OMG. So what about this situation? 17 actors were invited to audition for 6, right? I know we can all argue about how many Avengers there are. I consider, right? I'm just talking about the 6 for this problem, okay? Let's not, everybody hold on. Everybody just calm down. 17 actors were invited to audition for 6 Marvel Avengers. How many different ways can the director cast these 6 roles? Well, if I have 6 roles, 1, 2, 3, 4, 5, 6, but there's 17 people that I need to arrange. And once I choose Iron Man, that person can't be chosen to also be the Hulk, right? So what do I have here? I have an arrangement, which is a permutation. How many choices do I have? How many slots do I have? Right? So by formula, that is n, the choices I have, divided by the slots. I'm sorry, n minus the slots. So I can, right, the 11 factorials are going to cancel out. This is going to be 17 times 16 times 15 times 14 times 13 times 12 times 11 divided by 11 factorial by, and I have 17 times 16 times 15 times 14 times 13 times 12. So you don't have to use this formula if you don't want to, right? If you can figure out, right, this is just a, but I promise you, firstly, as your numbers get larger, you certainly want to know this formula, right? You have more choices and more slots, but your choices are still greater than your slots. And you have a calculator that spits this out very easily. How about this? A president, vice president, and secretary are chosen from a 25-member drama club. How many different ways can they be chosen? Once I choose the president can't be the vice president. So I have 1, 2, 3 choices. I'm sorry, I have 3 slots. And I'm choosing from 25. So I could just do this, right? But by formula, that is the arrangements of 25 people into 3 slots, which is 25 factorial divided by 22 factorial. Cool, right? All right, so we've done some counting. We've done some permutations, and we've done distinguishable permutations. Oh, I forgot I did that. Now let's talk about the addition principle. The addition principle just means more than one counting or permutation. So how many ways are there to arrange the letters in the word word? No repeated letters. So I don't have to worry about distinguishable. But I do want to make the arrangement start. I want one choice to already be done. So here's my first situation. I don't really need my permutation formula because I have the same amount of slots as I have choices. But I also have another situation. The first situation, I want to start with O. The last situation, I want to end with O. So if this slot is already chosen, what do I really have here? What can I choose here? 3 of the remaining, then 2 of the remaining, then 1. That's not a 0. That's the letter O. But that's 3 factorial, isn't it? But what do I also have? If I have the O in the last slot, 3 of the remaining go here, 2 of the remaining, 1 of the remaining, that's also 3 factorial. $12. So I added 2 arrangements together. What about this one? How many ways are there to arrange Paul, John, Ringo, and George? Does anybody know who those people are? In a line such that George is not last. So just like the first situation, I am saying I want a permutation, but I am fixing one of the choices. Now, there's oftentimes with these problems, there's more than one way to do it. Here's the way I chose. My first situation is George is not last, right? But I only want George is not last. I'm sorry. That's the only situation I want. George is not last. That's just one. Unlike up here, I had two situations that I wanted to add. Here, I have all the ways I can arrange. And what do I need to take away? All the arrangements minus the one where George is not last. So this one, and again, I have the same number of slots as I have people, so I don't need my NPR. I have 4 people, but once Paul is chosen, then I choose from John, Ringo, or George, right? So on and so forth. So that's 4 factorial minus, what's this situation? I don't want George to be last. Of all the permutations, how many of those, right? George can't go here, so no George. But what does that mean over here? How many choices do I have for this slot then? Well, I have George and 2 of the others. Once that choice is made, I have George and 1 of the others. And then once that choice is made, I just have George. So I have 4 factorial minus 3 factorial for this one. Yes, it's still the addition property because, remember, subtraction isn't real. It's just the addition of the opposite. Now, that's not 1 factorial, is it? 4 factorial is 24. Minus 3 factorial, which is 6. So my final answer is 18. So again, that's not the only way to do the problem. I could have done the problem literally with the addition and said, well, I could have basically 3 factorial 3 times, right? I could have just done right? George not last. So that slot is taken. So I just have 3 times 2 times 1. I guess I'll do that instead of the x. Plus 3 times 2 times 1 is another way. George cannot be last because one of these is George, right? But what is that? 3 factorial plus 3 factorial plus 3 factorial. Now that is repeated addition of the same number, so that is 3 times 3 factorial, which is 3 times 6, which is 18. Okay? Doesn't matter which way you do it. Anyway, any of these, so many of the problems in discrete mathematics can be done multiple different ways. You will probably come up with a way of doing some of the problems as we go through that, and you'll say, Ms. Getz, can I do the problem this way? And I'll be like, I don't know, right? Because there's so many permutations that I don't know them all. Do they work is the question. So now I'm just getting a little bit more messier, right? Adding a couple of permutations together, subtracting. Now arranging things in groups. So just recognizing with the words what's going on here. So this is sort of like back at the first problem where Victoria had 3 shirts and right, all that, and 4 pants and blah, 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 blah. So it sounds kind of similar. 3 science, 4 math, and 5 history books. Now, why wouldn't you have the most math books? Are arranged on a shelf. How many arrangements are possible? Now, if it just stopped there, I could do this problem. But they're saying how many arrangements are possible if the books from each subject are to be grouped together. So think about what that means. For that to be true, first I have to think about, well, wait a second. If the books are to be grouped together, how many subjects do I have? I want all the science books together, all the math books together, all the history books. How many different ways are there to do just that? 3 factorial, right? I can put all the math books here, science books here, history books here, or I can put all the, right? If I choose the science books here, I can't put them there, but if I choose the math books here, I'll put the science or the history, that, whatever. So there is the arrangements of the topics. But within each one of these, what do I have going on? In here, I have how many books? The 3 of the science books, right? So if I say this is a 3, 2, 1 doesn't go with science, but if I say science, math, and history, how many science books do I have? 3, right? How about in this bag, if you will? How many math books do I have? How many history books do I have? Right? Now, what are the different ways to order those? Right? How about inside each one of these bags, what's going on? If I have 3 of them, 3 books, how many different ways can they be arranged? How about this one? If I have 1, 2, 3, 4, and how about this one? So I have all these purples, 3 factorial has to be multiplied times 4 factorial has to be multiplied times 5 factorial, and all of those have to be multiplied by what? The 3 factorial from grouping them together. 10,368 ways to arrange those books, but grouping the science, math, and history ones together. Kind of crazy, right? Let's look at another one like that. Well, this is my fam last year. That's all of us. Right here, see here, look, this is D1, my oldest, that's Dean. This is D2, my daughter Deanna. This is D3, my son Drew. This is D4, my daughter Devin. She's the one that came up with the yell point. This is D5, my daughter Deanna. And this is, oh, did I cut Dylan out? Boy, where is Dylan? I think Dylan is over here. Oops, I cut him out. There's D6, Dylan, I swear he's there. And then these are my little grandbabies. This is Deanna's, Deanna's husband, Tim. This is Drew's wife, Allie. And this is Dean's girlfriend, Julie. This is Michael and Matthew, who are Deanna and Tim's. And this is Ella and Lucy. Right? My son's daughters. My son has 2 daughters. My daughter has 2 sons. Pretty cool, huh? Oh, and my daughter, Deanna, D2, is expecting her 3rd baby in May. I'm super excited. So this is my fam, except for poor Dylan. Sorry, Dylan. I didn't realize I cropped you out. Anyway, so there's 14 people here, minus Dylan. They sit together on a long bench. If the mom and dad, me and Mr. Getz, we want to sit together, how many seating arrangements are there? So there is a condition on what I want to happen. Now I have 14 people, so 14 seats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, crap. 11, 12, 13, 14. Is that 14? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 places to sit on the bench. So that's an awful lot, right? But I want to group the mom and dad together. So I have, right? I don't really have 14 factorial choices, right? Because I want to group these two together. So if that's one choice, how many do I have left? Right? In here, in this slot, can go how many of the people, not mom and dad, right? Mom and dad are taken care of. I'm going to put them over here. How many people are here? Good. So I think you can see that that's 12 times 11 times, right? What is that? I can write that much easier as 12 factorial, right? But I still have to take care of what's the deal in here? What's the deal in my bag? How many people are in my bag? 2. There's 2 people, mom and dad in my bag. So how many different ways can they be mixed? 2 factorial, right? But you're not done. Why aren't you done? How many different places can these 2 go? They have to stick together, but how many places can they, right? Can they go? 14? No. 13 different places, right? Not 13 factorial. There's just 13 ways that can happen, right? 13 ways they can happen. Kind of cool, right? Hey, hey, hey. This is all multiplication, right? What if I wrote it like this? Can you see what you can do right here? What is 13 factorial times 12? I'm sorry. What is 13 times 12? Oh, rats. Right. And again, you don't have to write it like this. The only reason this is called foreshadowing a little bit, this idea of how I can write factorials multiple different ways, that's going to come up in a couple of videos from now where we're going to do a lot of work with just factorials. No, right? No permutations, no counting, no whatever, just working with factorials. There's going to be a lot of this kind of different ways I can rewrite factorials can be super helpful. So it doesn't matter. I don't care how you write your final answer as long as I can see what you're doing. Have you taken care of the 14-person family? Really 15. And the condition that the mom and dad sit together. So you're not only grouping them, but you're talking about all the different ways that they can be grouped. I mean, that their slot can be taken up. Okay. All right. So that's a lot to digest for the beginning. So we will practice more of this in our live session along with the content from the next video, which won't be as long as this one. This was a longer intro. All right. I will see you in our next live session.